Euclidean geometry incorporates the concepts of distance and orthogonality. Let's consider the notion of a length of a vector in R2. So let's consider a coordinate system and suppose we have a vector here. So here we have a point P, and so what does it mean that coordinates of a point P is x, y? So this means that this point projects, so here at the point x, and here to the point y. And then, so if we take the segment OP, so what is the length of a segment OP? So here we use Pythagoras theorem, and we write that OP squared. So here we have a right angle triangle, right? And so the base of this triangle has length x, and the height of this triangle has length y. So what we have is that this is x squared plus y squared. So this is by Pythagoras theorem. Let us consider the same problem in R3. So suppose we have an orthogonal coordinate system in R3, and O is the origin, and we have a point P somewhere in space with coordinates x, y, and z. So how can we calculate the distance between O and this point P? So one way of doing this is we can drop the perpendicular from the point P to the plane xy. And then in this plane, so let's call this point K here. And let's connect the point K with the point O. And because we drop the perpendicular, so here we're going to have the 90-degree angle. And the length of this projection, so this, so what we have is that, so the length of PK is equal to Z, or rather absolute value of Z, because Z could be negative in principle. And so then what we can say is that if we consider the triangle OPK, so this is a right triangle, and then by Pythagoras, we have that the length of OP squared is equal to the length of OK squared plus the length of PK squared. Now, what are the coordinates of the point K here? So K is a point in xy plane, and so if P had coordinates x, y, z, then K will have coordinates x, y, 0. Right? So we drop down in z to 0. And so now, so we get here that by two-dimensional result, so we know that in this plane, the distance between O and the point with coordinates x, y, well, this 0 is irrelevant when we talk about xy plane, then OK squared, well, basically by this result here. So this is equal to x squared plus y squared. and pk squared is equal to z squared. So what we get is that if p has coordinates x, y, z, then the square of the distance from the origin to the point P is given as a sum of squares of the components, x squared plus y squared plus z squared. And we obtain this by applying Pythagoras theorem twice. Once to the triangle OPK, and the second time on the previous step when we calculated the distance inside the plane. And now it becomes clear how this generalizes to Rn. So if we take length of a vector in Rn, so if we have a vector v with coordinates x1, x2, xn, then length of v squared is equal to x1 squared plus x2 squared plus xn squared. And basically, so this is proved by iterated application of Pythagoras theorem. So here we need to apply Pythagoras theorem n minus 1 time every time going down in dimension. Now, if we have 2 points, right? So if this, for example, is a vector OP, and suppose we also have a vector OQ, which is y1 through yn. Then, so what is the distance between points between P and Q? So this will be the length of a vector PQ squared, right? And so here, this vector is obtained by taking coordinates of the point Q and subtracting coordinates of point P. So we have y1 minus x1, dot, 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 yn minus xn. So this is the vector PQ, and then we take its length squared. And we get the following formula, that the length between points P and Q squared is equal to y1 minus x1 squared plus y2 minus x2 squared plus yn minus xn squared. Next, let us define dot product in Rn. Suppose we have 2 vectors. Say we have a vector u with coordinates x1 through xn, and the vector v with coordinates y1 through yn. So the dot product of u dot v is defined as the following expression. It's x1 times y1 plus x2 times y2 plus xn times yn. The most important property of dot product is that it is related to the length of a vector in the following way. If we take a dot product of a vector with itself, then the expression will be x1 squared plus x2 squared plus xn squared. And so what we see is that the dot product of a vector with itself is equal to length of this vector squared. And so this is an important property. But dot product also has additional nice properties. So here they are. So this is called bilinear properties of the dot product. So 1, when we have a dot product of u with a sum of 2 vectors, v plus w, then this is equal to dot product of u with v plus the dot product of u with w. And 2. When we have a dot product of u with a constant multiple of v, then this is the same as k times the dot product of u and v. So here k is a real scalar. And also dot product is symmetric. So this means that the dot product of u with v is equal to the dot product of v with u. So that's immediately follows from the definition. And as a result, so there are two properties that are symmetric to these ones. So we can call them 1 prime is that if I have u plus w dot product with v, so this is u dot product with v plus w dot product with v, and 2 prime if we have k u dot product with v, this is the same as k times dot product of u with v. Next, we're going to explore a connection between the dot product and orthogonality. How does Euclid define orthogonality? Suppose we have two intersecting lines, and suppose they intersect at a point O. And here we have a point on one line, P, and a point K on the other line. So according to Euclid, so lines OP and OK are orthogonal or perpendicular if the closest point to P on line OK is the intersection point O. So this basically means that if we have a perpendicular here, then this perpendicular is shorter than any slant here. And so this means that if we have two intersecting lines, then they intersect at 90-degree angle precisely when the point of intersection is the closest point on the other line to the given point P. Now, imagine that the lines were not orthogonal. So suppose we have a point O, here a point K, and a point P. Then in this case, the closest point on the line OK to the point P will not be the point O, but will be some other point. This tells us that there is a connection between orthogonality and distances, and thus dot products. Let's measure distances from point P to various points on the line OK. So for this, we introduce vectors. So suppose this vector OP, let's call it U, and vector OK, let's call it V. So if we take some point S here, then this vector here can be written as T times V. So it's a multiple of this vector V, right? And as T varies, so when T runs over real numbers, then the point S will run over this line here. Let us write down what is the vector PS. So the vector PS can be written as PO plus OS. So PO is negative of OP plus OS. And so this is negative U, and OS is T times V. So let's compute now the distance PS. So the distance PS squared is the square of the length of this vector, and we know that this is the dot product of this vector with itself. And so if we substitute this expression, then we have TV minus U dot product with TV minus U. Now, using linearity property that we have discussed, so this is equal to T squared times V dot V minus TV dot U minus TU dot V and plus U dot U. And so this simplifies to T squared times length of V squared minus 2 times T, the dot product of U with V. Well, the dot product of U with V and V with U are the same, plus length of U squared. So what we obtained is that as T varies over real numbers, the length of the segment PS varies as a quadratic function in T. Now, let us recall one simple fact about quadratic polynomials. A quadratic function, polynomial, AT squared plus BT plus C with A greater than 0 has minimum at the point T equals B over 2A. Let's apply this result to this calculation that we've got here. So what we see is that we have minimum distance PS happens for the following value of T. So when T, according to this formula, it's minus U dot V over length of V squared. So for this value of T, this quadratic polynomial has the minimum, and hence this value of T will give the closest point on the line OK to the point P. Now, our question is when these two lines are perpendicular. And so here, according to Euclid, these two lines are perpendicular when the closest point to P on the line OK is the point O. But the point O corresponds to the value of T equals 0. So this tells us that this function has a minimum value at the point O, and that is at T equals 0, when the dot product of U and V is equal to 0. So we get this conclusion. Vectors U and V are perpendicular if and only if the dot product of these two vectors is equal to 0. So this becomes the condition for orthogonality of two vectors. This argument applies not only to R2, but also to R3 and to any Rn in general. Let us explore what are the ramifications of this fact for the geometry of lines and planes. Consider a plane in R3 with the following equation: x plus 3y minus 2z is equal to 0. So we point out that this plane goes to the origin because clearly 0, 0, 0 is the solution of this equation. Now, an interesting fact is that this equation can be written as a dot product. So it's a dot product of vector 1, 3, negative 2 with the vector x, y, z. And the right-hand side is equal to 0. So if we compute the dot product of these two vectors, then we precisely get the left-hand side of this equation. So what we obtain from here is that a vector u x, y, z belongs to this plane precisely when the dot product of 1, 3, negative 2 with u is equal to 0. But we know that dot product of two vectors is equal to 0 exactly when these two vectors are perpendicular to each other. So this means that u is perpendicular to the vector 1, 3, negative 2. Now, this means that all vectors in this plane must be perpendicular to the vector 1, 3, negative 2. So what's the geometric meaning of this vector? So the geometric meaning of this vector is that this is a vector which is normal to this plane or perpendicular to it. So here n is 1, 3, negative 2. So this is a vector normal to this plane. And the equation of this plane can be written as the dot product of n with u is equal to 0. So if we are given an equation of the plane, then we can immediately read out the coordinates of the vector which is perpendicular to this plane by just taking the coefficients at x, y, and z. Suppose now the right-hand side is not 0. Suppose we have another equation, x plus 3y minus 2z is equal to 5. So what can we say about these two planes? These two planes are parallel, and the way to see it is that suppose we just take these two equations together. So together, these two equations will form an inconsistent system because the left-hand side cannot be simultaneously 0 and 5. So this means that these two planes have no common solutions. And the only way for this to happen is that when these two planes are parallel to each other. And if these two planes are parallel, so this means that they have the same normal vector. So these are two planes with the same normal vector, and the only difference that one plane passes through the origin and the second doesn't. And so what we can see is that so this plane also has normal vector is n, which is 1, 3, negative 2. So the normal vector is determined by coefficients at x, y, and z, and not by the right-hand side. This idea applies to any Rn, and in particular we can also use it in R2. So suppose we have a line in R2 given by equation 3x plus 5y is equal to 10. So what is a vector normal to this line? So then the vector normal to this line can be read from the coefficients at x and y. So what we get is that the vector 3, 5 is perpendicular to this line. This little fact is extremely helpful when we solve problems on geometry of lines and planes. As an exercise, let's do the following problem. Find a point Q on the plane with equation 2x plus y minus 2z is equal to 5, which is closest to point P with coordinates 1, 2, 3. How can we find such a point Q on this plane? To do this, we need to drop a perpendicular from the point P to this plane. And so find an orthogonal projection of point P to this plane. And so this will give us the location of point Q. Now, what helps us here is that we actually know the normal vector to the plane. So from the equation of the plane, we see that the normal vector is going to be 2, 1, negative 2. So this will be a vector normal to this plane. But then this is the directing vector of this line. So what we get is that the line which is perpendicular to this plane through the point P has the following parametric equation. So it can be written as P plus T times N. So here N is the directing vector of this line and P is the initial point. And so because the directing vector has to be perpendicular to this plane, so we can choose N to be the directing vector. Now, to find the point Q, all we have to do is we need to find the value of T for which this point will be inside this plane. So basically, we are looking for the point Q of intersection of this line with the plane here. Now, what is the equation of this line? So we have, so this line is 1, 2, 3 plus T times the normal vector 2, 1, negative 2. So this tells us that x is equal to 1 plus 2t, right? So we just add this. Y is 2 plus t, and z is equal to 3, negative 2t. So now we need to find the value of t for which these x, y, and z will satisfy this equation. So what we do is we just substitute x, y, z from the equation of this line into the equation of the plane. And what we get is 2x plus y minus 2z. This equals to 2 times 1 plus 2t plus y is 2 plus t and minus 2z, which is 3 minus 2t. And this must be equal to 5 because this is the right hand side of this plane. Now let's simplify this. So what do we get? So here we get 4t plus t, that's 5t, and plus 4t, so we get 9t. And the constants are 2 plus 2, that's 4, minus 6, that's negative 2, and is equal to 5. And so what we get is that t is equal to 7 over 9. So this tells us that when t is equal to 7 over 9, so this expression satisfies the equation of the plane, and so this will be the intersection of this line with this plane. So this will give us the point Q. So the point Q has coordinates 1 plus 14 over 9, so this is 23 over 9, then y is 2 plus 7 over 9. So this is 18 plus 7 over 9. So that's 25 over 9. And for z, we get 3, which is 27 over 9 minus 14 over 9. So we get 13 over 9. So this is the point on the plane 2x plus y minus 2z is equal to 5, which is closest to the point P with coordinates 1, 2, 3. Now, finally, let us find the distance d between the point P and the plane. Here we obtained that q is equal to P plus 7 over 9n. And then this tells us that d, which is the distance between P and Q, is equal to the length of a vector 7 over 9n. So what we get is that d is equal to 7 over 9 times the length of a vector n. And what is the length of this vector? Well, it's a square root of the sum of squares of its components. So we have 2 squared plus 1 squared plus negative 2 squared. Right? So this is because the square of the length of a vector is the sum of squares. And here we get square root of 9. And so what we get is 7 over 9 times square root of 9. So this is 3. So we get 7/3. So this tells us that the distance between the point P and the closest point on this plane is 7/3. Let's do another problem of this kind, but now with lines instead of planes. Now, here we have 2 crossing lines in R3. So these lines are given by their parametric equations, and these 2 lines do not intersect. What we need is we need to find a pair of points, K on one line and L on another, which are the closest to each other. So this means that we have a perpendicular here and we have a perpendicular here. Now, let us recall what's the geometric meaning of a parametric equation of a line. So if we call this point A and this vector u, then A is some point on this line, and u is a directing vector of this line. So this means that u is going to be a vector along this line. And likewise, if we call this point B and this vector v, then what we have is we have somewhere a point on this line and a directing vector v of this line. And what we can think is that we need to find a value of t which will give us the point K, and the value of S for which this will become the point L. Now, the vector OK is given by this parametric equation. So this is OA plus T times U, where T is to be determined. And the vector OL from the second equation is going to be OB plus S times V, where S is also to be determined. Now, let us write down what is the vector LK. So the vector LK is equal to LO plus OK. And so this is minus OL plus OK. And so this becomes OA plus TU minus OB minus SV. So this is the expression for the vector LK. And what do we see from this picture? What's the condition on this vector? Well, this vector must be very special. This vector must be perpendicular to vector u and to vector v. So what we get is we get constraints here. So the dot product of LK with U must be equal to 0. And the dot product of LK with V must also be 0. So here we're going to get two equations that will help us to find two unknowns, S and T. Now let us write down this vector LK explicitly. So to obtain this vector, we essentially take the coordinates of K and subtract the coordinates of L. So here we're going to get the following vector. It's 1 plus 2t minus 2 minus s, then 0 plus t minus 2 minus s, and 7 minus t plus 3 minus s. So we can simplify this to negative 1 plus 2t minus s, t minus 2 minus s, and 10 minus t minus s. Now, what is LK dot product with U? So U is the directing vector of the first line. So this will be 2 times minus 1 plus 2t minus s plus 1 times t minus 2 minus s and minus times 10 minus t minus s. And this must be equal to 0. Let us simplify this. So what's the contribution of t's? So here we have 4t plus t plus another t. So we get 6t. Then what's with s? So we have minus 2s minus s plus s. So we get minus 2s. And the constants are minus 2, and minus 10. So that's minus 14. So this is equal to 0. Now let's consider LK dot V. So V is this vector which has coordinates 1, 1, 1. So the dot product will be minus 1 plus 2t plus s, or minus s, then plus t minus 2 minus s, and plus 10 minus t minus s equals 0. And this simplifies, so we have 2t, 3t, so we have 2t, and then with s we have minus s, and minus s, minus 3s, and the constants are minus 1, minus 2, and plus 10, plus 7, equals 0. So what we've got here is we've got two equations with two unknowns. So let us solve this system. So the augmented matrix will be 6 minus 2, 14, and 2 minus 3, negative 7. So here what I'm going to do is first I'm going to switch row 1 with row 2. So this will give me matrix 2 minus 3 minus 7, 6, negative 2, 14. And then we're going to say R2 prime is R2 minus 3 R1. So we get the following matrix: 2, negative 3, negative 7. And then here we have 6 minus 6, that's 0. So negative 2 plus 9. So that's going to be 7. And we have 14 plus 21. So that's 35. So now we take the last row. We say R2 prime is 1 over 7 times R2. So we got matrix 2 minus 3 negative 7 0 1 5. And so now we need to create 0 here. So we say R1 prime is R1 plus 3 R2. So this will give us the matrix 2 0. So we have negative 7 plus 15. That's 8 0 1 5. And the last step is we say R2 prime is equal to 1/2, no, R1 prime is equal to 1/2 of R1. And the final matrix will be 1 0 4 0 1 5. So this tells us that the solution has t equals 4 and s is equal to 5. And so this tells us immediately what are the points K and L. So we obtain that OK is equal to OA plus 4 times U. So this becomes 107 plus 4 times 2, 1, negative 1. So what is this? So this is 8 plus 1, that's 9. 4 and 7 minus 4, 3. So this is the coordinates of the point K here. And OL is OB plus 5V. And so that is 2, 2, negative 3 plus 5 times 1, 1, 1. So that is 7, 7, and 5 minus 3, that's 2. Now we found points K and L on these lines that are closest to each other. And then the distance between these two lines is the length of a vector KL. And so this vector KL is equal to OL minus OK. So we take the endpoint and subtract the initial point. And so here we have 772 minus 943. So the vector KL has coordinates negative 2, 5, no, 3, and minus 1. So then D, which is the length of KL, is obtained as a square root of negative 2 squared plus 3 squared plus negative 1 squared. So this is square root of 14. So in this problem, we found 2 points on these lines that are closest to each other, and the distance between these two lines is a square root of 14.